Welcome back to Discovering Geometry with Mrs. Berry. This is lesson 58. In this lesson, we will talk about special right triangles, and we'll be looking at the Pythagorean theorem for those special triangles. One special right triangle is an isosceles right triangle. Can you draw what that triangle would look like? An isosceles triangle would have two sides the same length, and it would have a right angle. This is what it would look like. We have two sides here and here that are the same length, and we have the 90-degree angle across from which is the hypotenuse. This is used often in science or engineering because it is half of a square. These sides would be the same length, and so a square cut in half is this isosceles right triangle. It's also often called a 45-45-90 triangle because those are the measures of the angles: 45 degrees, 45 degrees, and 90 degrees. So let's look at an investigation with this isosceles right triangle. Sketch an isosceles right triangle. Label the legs L and the hypotenuse H. So here are two legs that are the same size, and our hypotenuse, which is H, and here's our right angle. Pick 2 for L, the length of the legs, and then use the Pythagorean theorem to find H. Then we'll simplify the square root if necessary. We will then use this table and repeat these steps for different values of L. And we're going to see if we can find a relationship between L and H. So the first time, if we pick 2 for L, our Pythagorean theorem would be a squared plus b squared equals h squared, our hypotenuse, our c squared. So 2 squared is in an isosceles right triangle. If the legs have a length of L, then the hypotenuse has a length of what did you find? It was L square roots of 2 every time. So the hypotenuse is the square root of 2 longer than either of the legs. Another special right triangle is made by folding an equilateral triangle along one of its altitudes. The resulting triangle has angles of 30, 60, and 90. We call this a 30, 60, 90 triangle. It also shows up often in mathematics and engineering. So this blue side is the 30, 60, 90 triangle, and you can see that it's half of the equilateral triangle. So let's do an investigation with this triangle. What is the measure of angle A and angle B? What are the measures of BCD and ADC and BDC? So if we know that we're starting with an equilateral triangle, then we know that these are 60 degrees. So up here, we also have a total of 60. Since it's cut in half, each of these will be 30. And down here, we have another right angle on this side. Is this ADC congruent to BDC? Yes. Because all the angles are the same and this line that cuts in the middle is the same for both, then we can say that the two triangles are congruent. You could use the angle side angle congruency. How do AC and AD compare? If DC cuts these in half, then we know that this one is congruent to this one. If this is an equilateral triangle, then AC and AB are the same length. If AD and DB are the same and they add up to AB, then we know that this is half. So if this is length A, then this is length 1/2 A. So let's choose any integer for the length of the shorter leg and use the relationship and the Pythagorean theorem to find the other leg and the hypotenuse. If we have the short leg being 2, that would be this part down here. That is half of the hypotenuse. So the hypotenuse must be 4. Now we can calculate what the longer leg is. So the shorter leg is our A. Our longer leg, we don't know yet, would be B squared, and our hypotenuse is 4 squared. 2 squared is 4, and 4 squared is 16. We're going to subtract 4 on both sides, and we'll have that B squared is equal to 12. We'll take the square root of both sides, and we have that B is equal to the square root of 12. 12 is 3 times 4. 4 can come out of the square root as 2 square roots of 3. So our longer leg is 2 square roots of 3. Let's pick a different number. Let's go with 5 for our shorter leg. If our short leg is 5 and our hypotenuse is twice that length, so our hypotenuse is 10. So let's calculate what that longer leg would be when the shorter leg is 5. So we have 5 squared plus B squared equals 10 squared. 25 plus B squared equals 100. Let's subtract 25 from both sides. B squared is equal to 75. We'll take the square root of both sides. B is equal to 75 is 25 times 3, and 25 is a perfect square. So the square root of 25 is 5. What's left inside is still the square root of 3. So 5 square roots of 3. Pick another number for your short leg and calculate the long leg and the hypotenuse. See what pattern you see. So in a 30, 60, 90 triangle, if the shorter leg has a length of A, then the longer leg has a length of A square roots of 3, and the hypotenuse was twice as long as the shorter leg, or 2A. So these relationships are good to know so that you can skip using the Pythagorean theorem and just put the numbers in If I know that the short leg is 7, then I know that the hypotenuse is 2 times 7, or 14. And then I know that the longer leg would be 7 square roots of 3. I can do all that without even using the Pythagorean theorem. Here's a picture of our equilateral triangle cut in half to make a 30, 60, 90 triangle, and the a square roots of 3, and 2a relationship. Let's do an example. Here's a picture where we have some triangles, and we have some right angles. How do we find G and H? I'm going to look here. I see what appears to be a rectangle. I want to double check that it is for sure a rectangle so that I can use those relationships. I have 90 degrees here on the opposite side of this one that's marked. I have a right angle here and here. 3 right angles means the last one has to be a right angle, so that would indeed be a rectangle. That means that I can say that if this side is 120, then the other side is also 120. And if this side is G, then it is the same as over here. So at least I can mark that this is congruent to these two over here. I see this triangle right in here, and I have 2 sides. I have the hypotenuse at 130 and I have the long leg at 120. So then I can calculate 130 squared is equal to 120 squared plus what would be G squared. Because not only is this and this are the same length, and so I could use even this bottom as G, it would be the same. So what I'm doing is saying that this is also length G. Now I recognize this as 10 times the multiple of one of our Pythagorean triples. So one of the Pythagorean triples is 5, 12, 13. So I see that in here. I see 12 and I see 13. And so G would be 5 times 10, or 50. And again, you can calculate that if you don't recognize all of your Pythagorean triples yet. So G is going to be 50. So that means down here, this is also 50, and this one is 50. And so to find H, I'm going to use this relationship of a 30, 60, 90 triangle. So this would be 60. If my short leg is 50, what is my hypotenuse? Well, my hypotenuse is twice the short leg, so my hypotenuse is 100. And I did that one fast because I recognize it as a 30, 60, 90 triangle.